Thanks, everyone. So please stop me if you have any questions. I'll start. I'm a research scientist at Michigan. I've been working on automated analog design and IC design in general. In this presentation, I will be presenting about Open FASoC, which is an automated open source analog and mixed signal IC generation that originated from the DARPA program called FASoC. So I'll go through that and give you an overview of the history behind it. All right. Okay. So I think it's important to give a little credit of the Open Road and FASoC programs, part of the DARPA programs. It was DARPA funded 4 years ago. It is a multi-university and industry effort led by the University of Michigan in collaboration with the University of Virginia and ARM. FASoC specializes in autonomous SoC synthesis, which includes all the building blocks such as analog generators, memories, and cores. And I have added a couple links here. You guys can go and check them from Dave Wenslow's talk last spring and or a year ago, and a couple other publications. So at a higher level, FASoC is short for fully autonomous SoC synthesis. It is a set of tools and scripts heavily based on Python and Tcl and writes on top of existing synthesis and physical design tools. We support usually adapted commercial tools, which allow us to build complete SoCs, designs, ensuring full integration of all the blocks. We also leverage IPExact to do both the stitching and floor planning, which was added as part of the IDEA program. In addition to that, the automated SoC generation, we also have a whole suite of analog generators that has been growing over time. And just since the FASoC program has started, we have added a couple which are highlighted in green on the following diagram. So over the course of the program, we have successfully taped out a good number of SoCs, as well as test chips containing specific analog blocks. Here on the left, you can see our first automated SoC in TSMC65, and it was successfully demonstrated at the last in-person DARPA summit at Salt Lake City. We have done a demo, and the students showed that the SoC is working with the DVFS scheme, so that was great. Since then, we I think someone is trying to get in. Since then, we have ported our generators to GF12 LP, which is a FinFET technology. We have done 2 test chips already. This one is the first one, and I didn't want to put all the test chips here, but I kind of summarized some of them afterwards, which are using open source tooling. So let me go through the framework and using both open source and closed tools, and feel free to stop me if you have any questions. So we are using a cell-based approach to analog design. You might have heard it a couple of times before, but it is a really simple way to understand this, or a really simple way to understand this is trying to describe analog blocks in Verilog. So and that can either be instructor or Verilog, behavioral, or a combination of both. So the Verilog is basically giving you the connectivity. It's similar to CDL, and you can use that to connect all the building blocks of your analog design. With the structure of Verilog, we plug in specific cells that are identified as the critical analog functions to a generator. This could be either from traditional standard cells libraries or a library that has been augmented with a couple of these cells that we like to call auxiliary cells. I have added circuit diagrams of analog generators we use in FASoC. All our structures have been taped out before and published in flagship conferences like ISSCC, VLSI, or CICC. These are legacy designs that have proven their results on other nodes. I highlighted in blue the example of auxiliary cells for designs like SAR ADCs, DLDOs, Temp Sensors, PLL, and switch cap DC-DC converters. Each time the analog function is either a header cell, a power switch, a flying cap, or a comparator. So then after creating a template of these analog structures, we use different automated ways of modeling the circuit so that we cover design generation for a wide range of input specs. The diagram on the left summarizes that process. This is a list of the required auxiliary cells. This list have grown since then, but it gives you an idea of what we call auxiliary cell. It is possible to get away only using standard cells, but your design is going to get performance hit, but a very fast port-in, which is great. Other times it's not enough, and then we need to add some couple cells to which is really equivalent to adding standard cell. Now, after interacting with Align, we started using their tool to automate the generation of these blocks, and that has been great. Usually I would budget for each of the auxiliary cells about 3 days to get something decent, sometimes more if you want to optimize your design. So now that we have a Verilog hardware description of our designs, then we have a shot running that through the digital tool flow and place and route to generate the final physical design. So I made a small workflow diagram on the left of what would be a traditional analog layout flow today. As you all know, most of it is custom and require multiple iterations from schematic entry to layout, then simulation, and so forth. While the digital flow is highly automated for a while now, and it's a low-hanging fruit to use for your framework. So the idea is to basically take what would otherwise be a full custom analog layout and shoehorn it into the cell-based digital automated design flow methodology, which is pretty amenable to the available logic synthesis and place and route tools, be it proprietary and even better open source tools. FASoC relies on a set of proprietary tools wrapped inside the cadre flow developed by Professor Ron Drezlinsky at the University of Michigan, and it is an abstracted layer on top of the Cadence Foundation flow. Using that, we have been able to build a really wide range of analog blocks, such as the one I mentioned before, digital LDOs, PLLs, sensors, CDCs, DC-DC converters. But here I would like to focus on the open source versions of our tools. Open FASoC relies heavily on OpenRoad, in addition to a set of other tools like UOSIS for synthesis. We recently started using the Verilog UHDM plugins to UOSIS integrated by Ant Macro and Google to add the system Verilog support. Magic, NetGen for DRC LBS. We have added K-Layout recently, which it appears to be a powerful tool for layout viewing and LBS and DRC checks, but also automation. And finally, we are using ngSpice, which is currently used for prospect simulation, but also XICE, which is part of the IDEA programs, DARPA IDEA programs. And coming back to physical design, it is worth noting that using OpenRoad, we are able to use Tcl-based or even better Python-based APIs to easily do things that are a little more complex using proprietary tools, such as building macro functions to do symmetrical placement or arrays or guard binding. I'll get to this later in this presentation. So I want to go to this section here, which is about trade-offs and examples of what is it we're doing in FASoC and how it translates in terms of result. So I really like this diagram, which summarizes where FASoC, which is using commercial tools, is today. So if we take full custom layout, which is all the way to the left with 100% complexity, and compare it to the initial version of FASoC 1.0 started 3 years ago, which is on the right. And it uses minimum constraints without any custom placement or anything in APR tools, then obviously the complexity goes way down. However, we can see that the performance takes ahead compared to high-end analog design. Now, when we swing back into the middle, where we use partial constraint and digital compensation to address non-idealities, this still reduces complexity a lot to fully custom flows and tools. And we gain back a lot of the lost performance in loosely constrained approach. So we kind of get the best of both worlds. In fact, in using our cell-based approach, we are in reality avoiding the extreme complexity of trying to take in all the PDK DRC rules that comes in with full custom automated layout like routing or active layers drawing. Also, with the rule of diminishing returns, the time required porting to a new PDK or even a new design topology would essentially make an automated full custom analog generator too costly to make across PDKs and test cases. So I think we have here a sweet point which I fundamentally believe we could push a little more to the left here when using open source tooling, and I'll get there later in this presentation. Here's a few examples of what constraints would look like for a PLL, where we give extra attention to the DCO block. We are using Python scripts to structure the placement of fine and coarse cells, where all the cells are sitting tightly on a fairly wide stages. The DCO sits on the right in the middle of the rest of the PLL, which is all placed and routed and surrounded by end caps and D caps. These blocks has been taped out and has been published recently in RFIC. Another example is for power regulation, digital LDO, which we taped out in different technologies, including Skywater 130 and GF12, and I believe TSMC 65. You can see the pre-pack simulation of the max load current versus the array size of the PMOS switches, where everything looks fine and smooth. But then after running the design through APR with minimal constraints and random placement, we can see that post-spec simulation that the max load current takes a hit and goes way down. And as we increase the array size, we can clearly see the variations and resistive effect due to narrow routing and minimal VI cuts. But then after coming up with a more structured placement of the switch array, as well as fencing some of the cells, we also did automatic PDK parsing of its metal stack info to calculate resistivity over the power stripes mesh. This was done by Yash from Dave Wenslow's group. We can see that the performance is considerably improved with the smooth curve we see in prepex, as well as getting back the max load current, as you can see on the right plot here. A last example of what constraints look like for our SAR DC, we have implemented the Python script to achieve a common centroid placement strategy with the symmetrical placement of the unit caps and switches. This has been taped out in GF12 as well. So in addition to these GFPDKs and closed tools FASoC approach, a considerable part of the work we have been doing has been centered around the publicly released Skywater 130 nanometer PDK. Now we've done a couple tape outs. The first one was basically quick port of the temp sensor using we targeted the temp sensor, which was something I was actively working on. We have had the chance to tape out our design, the first shuttle, which consisted of 64 sensors using multiple VTs so that we could test the full capabilities of the devices on this PDK. We also taped out a digital LDO without a voltage reference, though, but it was targeting a 1.8 volt max load current of 25 milliamps. And most of the steps were using open source tools, except the pad ring and some of the verification. So this was when, this was before the release of the PDK. A couple months ago, we tested our chips from the MPW-1 shuttle containing the 64 sensors. A few things I would like to note here. We have implemented our aux cells with small circuit tweaks to just for wide input specification range, like temperature range, resolution, and conversion time. We have automated all of our testing scripts, and we provided our testing flow to the community so that they could reuse our sensors. Such generators are really great for early design space exploration, where we can predict performance in a new node very fast and would be useful for companies like foundries, or startups. The sensors are showing inaccuracy around 0.5 degrees C for the best chips, which is really state of the art. So we published this work in the solid state circuit letters. And our plans for the next shuttles is actually to improve the placement. I think I have a slide regarding that, but this is a summary table and comparison table to other projects. So as you can see, it's basically competitive to other blocks, and it's actually quick port. On the second shuttle back in summer 2021, we have tried to step up our game by including the demonstrators for our generators. So one of the achievements was to have a fully open source end-to-end flow for all these generators. In fact, since we are part of the OpenFASoC team, we were able to develop physical design tool features that allowed us to have that. The sensors were integrated with the OpenTitan SoC, powered up by one of the LDOs. We also improved the digital LDO design, which includes now a voltage reference, localized MIM-based decap cells, and arrays of LDOs supporting multiple loads, current loads, and using different implementations. So we have integrated 4 temp sensors. Those are supposed to be improved since the 64 array sensors. They are connected to the OpenTitan's IBEX core through the tie-link bus, a system bus. And as you can see, we were able to create voltage domains. That was the first implementation using OpenFASoC. And we had the sensing elements of the temperature sensors generator sit on a separate area with its own on-chip generated voltage. Non-default rules have been also enabled in OpenFASoC. We added on top of that Python scripting to connect customness to power ranks, which you can see on the left, which is essentially doing special routing. So basically here. All of these features are expected to be included directly in OpenFASoC. Some of them are already there. Actually, there's some work done by Peter Gatford and the OpenFASoC team on including a simple UPF flow. So that would be great for a lot of our designs, but also for low power design in general. This model seems to be working great following the software model with a lot of iteration and improvements. So when we get the chips back, we'll be able to see if our changes have been improved. But the next tape out we have, if you can see here, a lot of the placements are of the cells is random. So our goal is actually to have a structured placement of this temp sensor, which actually is going to give really good results. We have made 10 versions of the LDOs, as I said, using the digital LDO generator. In the second channel, we have included highly trimmable voltage references to take into account variability and PVT variations. As you can see, all the switches and voltage references structured are tightly placed using an evenly distributed placement to minimize variations. The power stripes for the switch array is created to minimize the resistivity as described earlier in this presentation. The OpenTitan SoC includes a UART, SPI interfaces, and in addition to 60 KB of SRAM thanks to the OpenRAM team. We have selected one of the digital LDOs to power up the SoC and its peripherals. Although the connection between the two was manual, we are excited about this project since it would be our first open source fully automated MS SoC. The OpenTitan SoC is our current demonstrator. We plan to tape out many other versions that would improve the overall PPA in open source design. So in general, we focus in our lab on low power IC design, improving the energy efficiency in general. And to achieve that, we expect this to be an iterative process over tape outs, automation, and tool updates. Speaking of energy efficiency and PPA, we have spent a considerable amount of time on verification and check-in timing. I think we were one of the last contributors to this second shuttle. And the reason is that we have given an extra care to closing timing. We had to use the latest timing features of OpenRoad in addition to the newly developed ECO flow to ensure our Fmax isn't impacted by all the margining on clock uncertainty. So briefly, as you can see on the diagram on the left, we noticed that the tool had a hard time fixing timing post CTS or even post routing. After doing many iterations using both clock uncertainty and margining, the Fmax was considerably altered or even worsened our hold violation. So our ECO flow used downsizing buffers on specific paths or added buffers. As you can see, we were able to fix our hold violation without losing any of our target clock of 20 megahertz, which required over around 5 iterations. Please note that this is solely using OpenRoad for physical design and timing improvement. So the other thing I'd like to mention here is that as a part of as a members of the OpenRoad team, we have tried to develop an OpenRoad to drive OpenRoad to include features that would enable Open FASoC generators. We have enabled commands such as create voltage domain that allowed us to have a fully open source temp sensor. An example of that is shown on the die photo on the right, and I have added the functions we had to add or update to achieve that. So some of these here might have been updated recently due to the work from Peter Gadford, which is really exciting. And I would encourage EDA developers to take a stab at it as well and help us improve or add new features. So pull requests are constantly being reviewed, which is a great way to have a thriving open source ecosystem. So now coming back to the performance versus tool complexity trade-off illustration I have shown in the intro, we have noticed that open source tools allow much more automation and control in general. As you can see on the illustration here, this allows to tremendously reduce complexity of our flow in other words, we push the limits of performance a little more to the left. In the case of the temp sensor generator, being able to control open source place and route tools to generate exactly what we need, as I have shown in the previous slide, allowed our generators to match the results using proprietary tools. The 64 instances of the implemented temp sensor are actually showing better results. So the point here is that there's a huge community of software developers in the open source world, and these members are really great with automating things, and we have been leveraging a lot of that to improve our generators. So now another tape out I wanted to mention is partially using open source, and since it was using GF12, so we didn't have access to verification or some of the flow steps. So we basically used OpenRoad to get this tape out done, and it was pretty exciting because it was the first tape out done in a FinFET technology and such an advanced node. We're able to reach a sign-off frequency, which was verified with closed tools of 350 megahertz with the corner above. And the sensors are actually showing really great results with 0.2 degrees C inaccuracy from a -20 to 100 degrees C post-spec simulation. And that is due to the FinFET being a very structured, physical design, right? Like analog doesn't allow a lot of customization in FinFET technologies. So here, now I'll move on an update on Open FASoC on the latest projects this year. So one of the exciting projects we've been working with NIST is around quantum, right? And the limitation here is basically that we need to interface the control system with the quantum processor, which runs at 20 millikelvin, with a system that runs at 300 Kelvin. So the idea that came here is that we need to create models that would allow us to design at this low temperature. So basically creating cryogenic temperature models. So this is the first step to start making a control system. And as you can see, we need inverters, ring oscillators, voltage references, low noise amplifiers. So this is basically the requirement. This is where the quantum processor is running. This is the building block to interface, and this is our nominal condition. So this work is being done with NIST under the Google NIST partnership or umbrella. Basically, two things are important here. So we try to recharacterize the Skywater models to enable really enhanced models for people to design it for high-end analog design. And the other point is basically to create models that for Kelvin, so people can design some of these building blocks for to interface with the quantum processor. And finally, this is all needs to be automated because the goal is to do this for different technologies, not only Skywater 130, but other nodes such as Sky 90, which was publicly released recently. So one of the constraints of these test structures is that the probes needs to have around 40 micron distance. So the structures are small, but they need to be squeezed in there. The reason is because of the probe card that looks here, like the picture on the right. So using OpenFASoC, we started using GDS Factory or called it so that we start using more customized design. And that was an enabler for OpenFASoC because we started doing things that we didn't do before. And the reason it goes back to the enabler, which is automation in open source. So these are some of the structures, the like line resistance and VR resistance, which are fully automated. There's also the structure here, where we use OpenRoad. We use depth manipulation using Python, which can be integrated within OpenRoad. I think it's in the process of being integrated. But basically, the limitation here is that the ring oscillator needs to be interleaved to minimize the variability. And then you have a counter here that sits in a different region. So we were able to do that using a Python script. It matches actually the PLL work we have been doing. And you can see that it's fitting between two pads, which is basically 40 micron here. So we have done this for multiple VTs in the Skywater PDK. So there's 3, 1, 2, 3 plus 9. So basically 12 standard cell libraries and different version of the ring oscillator as well. So you can see here, these are all automated and can be used for process variability as well, or process centering monitors. The other blocks are MEM caps arrays and transistors arrays, precision resistors, via line resistance, and diode modules. So all those were integrated. And for the MEM cap, for example, and this is what we have been using since then for things like the PMU or the SAR-ADC switch cap arrays. One of the major goals was to ensure balanced connection across all the caps. So the usual OpenRoad or APR approaches would not be able to handle this type of layout generation, especially the open source one, which is lacking. You could still do that with closed tools, I believe. So we chose to use GDS Factory to help create that layout. We have created several custom scripts that I would like to package them as routines. Each routine is designed for a specific task, but also be reused on other designs with different scales, different sizes, different cells, and different goals. So you can see here, we have different inputs, mesh dimension, pitch, layers, and this can be reused for each of the design that uses arrays, like flying caps or switches, as I said. Once the core of the design is ready, we call upon another routine called the pad ring and place and route routine, and which takes in the paths and the design and performs semi-custom connections between the paths and the design. Over the process of generating the MEM cap, the structures boil down to these few steps using the routine to compute and place small capacitors, diodes, or switches, or transistors, sorry. generate the connecting mesh metals, replicating the structures as needed, and connect the design to the test pads. So all of this have been reused in in the next project that I'll mention later. But just to end this part, this is the resultant test die. We had over 1,400 pads, 400 plus transistor structures, 30 capacitors test structures, ring oscillators, and line and via chain modules, and 7 diode test structures. So this has been done with NIST. Teams Ansel Group at Google, and IDSR from Israel, and Coolcat from Atkins Group. What is the plan here? After that is basically to test these structures at nominal condition, but also at cryogenic temperatures. And some of this fitting that has started already. So this has been tested at cryogenic temperatures by Akin. So we are on a, I think, and recently there was this Cower PDK raw data that was generated, so you guys can go take a look. I think Boris have shared some notebooks to try and explore the data, so that was great, and hopefully you can see more of that. So there are more generators. One of them is the secure and programmable PMU with power obfuscation. We have been working on the past semester in our class. So the PMU is basically, the goal is to have a programmable PMU for anyone in these projects or shuttles to use for their own, goals, right? So having a digitally controlled PMU generated for different requirements and with the possibility of being shut down as needed will add much more secure software control over the chip. The capability would also weed off a lot of the malicious downstream users by selectively turning on and off the blocks on chip. We have ported this design based on previous topologies of switch cap network to build programmable DC-DC, GF12, and TSMC65 LP designs. The proposed system has a reconfigurable or recursive and reconfigurable switch cap DC-DC converter that is composed of 6 stages of 2-to-1 converters. Its output voltage resolution is approximately 10 millivolt, and we have used this topology to create a new DC-DC converter that we have taped out in GF12, and I will show you the silicon result next. So this is the first generation of the DC-DC converter, which we used to tape out a single version of it with the spec described here. The desired output voltage 0.5, so the DC-DC converter has 3 stages. The number of input caps are 160, and the number of switches are 35, and the generated Verilog netlist in the generated Verilog netlist. The post-spec simulation shows around 75% efficiency at 0.5, while we measured around 68%. The proposed PMU with power obfuscation is including 2 blocks, main blocks, or additional blocks. One is for noise injection module, which takes advantage of random current patterns to hide power signatures. The second one is the DC-DC generator, which down converts VDD to any requested voltage. Here's the Verilog configurator module generation flow. First, we generate the truth table using Python. Then, after using the tools like Espresso, Sys, and ABC, we arrive to our we get our final Verilog. The Verilog module has passed BCS verification, and also the CDL version of it or extraction gets the right results. This is a more simplified flow. It's actually pretty easy. So we start from Python and finally APR. And on the right, we show an example of the generated result using OpenRoad. As essential part of the PMU is the auxiliary cells. And the auxiliary cells are like standard cells, but they also perform the mixed signal and analog functionalities. For the auxiliary cells, we are using aligned cell generators on the left. We can see that the converter slide schematic on the left and the layout on the right. This doesn't look like a standard cell, because we are using the custom approach of using mesh, the mesh arrays that we used for the NIST tape out. So that was great to include more customized blocks in our design. One additional point. So as you can see here, this is using a line which is supposed to be a fully customized tool. It's great to get a first sense of your design, but just an idea is if you're porting this block here, this would take you about a week to get to this result. We are not experts using a line, so we've been working with Sachin's student to get this done. And one of the next steps is basically to squeeze this design to gain in terms of density. So you can see here it's not dense at all. And the reason is because you have PMOS and NMOS switches, and it's either you place them as a standard cell, which is much more dense, or you need to find a way to tell the constraints that you need a little more, density here. The other block is the strong arm latch that doesn't look really great, but it gets you a layout out. So we're trying to work with Sachin's student to get this, to improve this generation here. Once we have gathered or generated all the cells, we extract and simulate the cells and obtain the current map as well as the results. Those results are combined with the user specs to calculate the different generations and configurations. Now, with the netlists and cells ready, we use the Open FASoC flow, which is built on top of OpenRoad. The first version of the result is shown on the left. You may see that the placement, routing, and power planning was challenging, to say the least. So we come up with a proposal to arrange the cells in the organized manner I've shown you for the NIST tape out. So basically, we have power muxes, arrays, switches, and flying caps. So now, after working through the flow, we obtained or used those routines. We were able to generate arrays, but we still had the issue, which is basically the routing. OpenRoad is made for digital routing, and even with using non-default rules, we still have narrow routing and short. So it was really a nightmare to get it done in OpenRoad. So I believe this is going to be resolved in the future, but this is the current status. So what we have done is basically we created this converters 2-to-1 converter slice. We created a mesh or adapters that are basically cells that we put on top of this cell here. Why we do that? The reason is because we want to be able to resize these transistors here to cover as much as possible of the design space exploration. So now when you put this mesh on top of it, the goal is when you increase the sizes of the transistor, you'll still be able to connect correctly to this mesh. So that was a bit of work, but it's actually reusable. So it can be used in different other designs like the SAR ADC or even the LDO. So that's the current approach we're taking. Now, when you put everything together, it just abutes like any similar to an SRAM, which is great, and you gain in terms of density. And you can see that you can upload the design inside the OpenRoad GUI, which is a great way to check if your design is connectivity is right. And you can see that when we highlight the routing, everything is connected correctly. That's another challenge, which is interoperability of the tools. So we're trying to improve that currently, but it's still there's a lot of work to be done there. So the flying caps are on metal 4 and 5 above the switches. One thing we can do is actually use the MIM caps and put them on top of the switches if you use the metal 4 and 5, which will gain us much more density. These are spice simulations in different voltages. Those are just actually these are C extract. We couldn't get the RC extraction right. I actually got it right recently, but these are the simulation using the C extraction, the coupling, basically. So in general, in summary, this is the PMU layout generators from 0.1 to 10 milliamps. We used intelligent placement for variant design specs. This would enable us to do design space exploration, but exhaustive design space exploration, I don't think that has been done. So basically, we're trying to get as many layouts as possible and use the compute power from GCP to generate as thousands or hundred thousands of designs, and then pick the ones that works for us. I'm excited about that, but basically this is a summary of the tools we've been using: Open FASoC on top of OpenRoad, GDS Factory in the red here, and Align for the auxiliary cells, and then Magic for some of the P cells, and K-layout basically, which is called by GDS Factory. I think I missed. All right, so this is the PMU. I put the star recursive diagram at the bottom here. We have included the closed loop pulse width modulation, noise injection techniques for side channel attacks mitigation. The reason for that is because we're doing OpenTitan, which is a root of trust, and also the thing that I'm excited about is the cell design space exploration flow. So I've showed you earlier that in green was our flow, basically using the digital implementation flow, but using these open source tools and community, we were able to use multiple other tools like Align, GDS Factory, and we were able to generate new, routines that can be used by a lot of other people, and that can help you design your mesh or routing, like special routing, for instance, for power routing. So there are new projects currently working on. I'll mention a few. So I'm working with a couple people from different places on a SerDes design. We're currently tackling the PLL, so we're using an LCD DCO. I believe we'll be able to put down something for the September shuttle. The other important block in this SerDes is basically the CDR, or clock and data recovery block. And that's been worked on by a team here in Michigan. So Professor Wenzloff is helping with his students, and also people like Chandru, who's very helpful, and some other people. The other project here is actually still in progress, but basically this optical phase array requires a lot of DACs, like 156 DACs and OTAs and TIA, sorry, transimpedance amplifiers. And we are basically working on generating those for Joaquin from Google, so he can use that as on the ASIC part of the photonic IC. So that's an exciting project we're currently working on, and hopefully we'll get more results or discover new things with this project. So this was my presentation. Thanks, Mariana, and everyone for having me. Please let me know if you have any questions.
Okay, thanks, Mehdi. So please, now the floor is open for people in the call. I'm sure you have a lot of questions for Mehdi. This was like impressive presentation and a track record, and I'm very much to say I really like the idea that where you kind of combine other people's approaches to mitigate the limitations of your initial kind of approach. So that means Align and GDS Factory. So I will start with the first question. So how much time is I believe that you probably work with your students on some of these topics.
Yes.
So how much time is actually necessary for somebody to get onboarded, like in the complete, let's say, approach, or they are like partially specialized for certain pieces, or how does your team work?
That's a good question. So analog design is like a wide range of things you need to know, right? And we can't be expert in everything, right? Even the experts in analog design, they are expert in something, right? Like ADCs or PLLs. I mean, some of them are really good at everything, but it's very rare. There's just a few people in the world that are really good at everything. So the way I'm working is basically try to collaborate with other people, like Professor Wenzloff from Michigan. He's an RF expert. He works on clocking, like PLLs. I mean, I can do my own thing, but if I want to make my design better, I need to communicate with him and have a regular meeting with him to get his feedback. I also reached out to a lot of people, like for instance, recently Philip from INRIA, who I met at the free conference, and he's a great resource, right? Like he's very motivated and he knows about radio. So one of my goals is basically to do a BLE in this technology and enable other people to use beacons and stuff like that. So, you have to be able to reach out to other people or have different, for instance, with my students, I have students that are very good with power management, and we can find a lot of those in Michigan, but also in clocking, there's students that like to do clocking, so I'd work with those to do this type of job. But also you need people who are good with software, right? So you basically try to get 1 or 2 students from CSE, so you can combine all those expertise and get the design out. Now, regarding the question of getting someone on board, using proprietary tools, so it is easier because everyone has been using those tools. But the good thing, if you get someone like the one you have, I think I know some of the one at the bootcamp, they have been using the open source tools. So I believe they are really good with OpenRoad, tools like OpenRoad or GDS Factory or Magic, and I'm pretty sure they can be onboarded really quick if you have a regular meeting. Um,
Yeah. But maybe my question was more like how much time does, people at your team, when they get onboarded, how much time is necessary, for certain approach? I'm just interested because, I want to compare it with, with the complexity that we're having within this programmatic IC design approach that is more kind of specifically tailored to analog.
Sure.
As a just a comparison and, to what you showed us.
Yeah. So I mean, so it's kind of hard to say, right? If you're building a new generator from scratch, then it's gonna take you time, especially if you need to come up with a new idea. If you just want to port your design from an existing generator, then I would believe a month should be doable for someone who didn't do any, like who doesn't have experience from the Open FASoC. If you want to do the temp sensor and port it to, let's say, 90 Skywater 90, I would believe like a week for one of my students should be enough if he's working hard. If he's taking his time, should be 3 weeks, right? But that's the general rule I have. Like whenever I get a new student, I want him to run the temp sensor as soon as possible. And if there's a bug, he should be able to do it. And one of the criteria to onboard someone is basically to give him a bug in the temp sensor and let him figure it out himself. And I think that's a good way for him to learn. So yeah, I know it doesn't answer fully your question, but that's the experience I have.
Yeah. Thank you.
Yep.
Any questions from the audience? I mean, we
Can
have a
you
unique
hear?
opportunity to ask Mehdi whatever. Let's use it.
Hi, Mira. Can you hear?
Yes.
Yeah, hey, this is Thomas Parry. I have a question. I was curious, the kind of approach pushes you from linear circuits more into continuous time digital circuits. I can see why that saves time in the layout, but I'm curious how that plays off in verification, because you basically always push to transient simulations, which means your verification could take longer. I was kind of curious if you had an opinion on the trade-off between those two. You understand my question?
Can you say that again, Thomas? It's kind of cut in on my side.
So if I understand the approach correctly, you kind of get pushed from linear circuits to continuous time digital circuits because you kind of prefer to use digital circuits from the analog perspective, so from the layout perspective. But as a result of that, you basically then have to start verifying everything in the transient time domain and not use like DC or AC analysis. So that maybe increases the time you have to spend in verification.
Yeah. So right, that's a good point. So for the PMU, okay. So for I just want to correct something. We still do AC simulations for the PLL and RF designs. I think Prof. Wenzloff would be a good reference here to talk about it because he's the one who's leading that. But regarding your question, like for the PMU, for instance, one of the simulations takes about 2 days. You know, in GF12 using closed tools. With in Skywater, it's taking, I don't know, either, you know, depending on the extraction you're making, from 8 hours to, you know, a day or two. So one of the nice things we want to explore is, you know, using the compute power from GCP. So Google provided us with that, and we want to use XSPICE instead of ngSpice to basically prioritize all these steps. And the goal is basically, instead of waiting for a day, 24 hours, basically to run that in an hour, or let's be wild, let's say 10 minutes. I mean, if it is able to be parallelized and used correctly, then we should be able to do something like that. So let's stick with 1 hour, and that would be tremendously helpful, because if we take the approach of generating hundred thousands of designs, we should be able to simulate them. And if we're gonna, it's not scalable if not gonna be able to verify the design, you know, within a couple, you know, hours, right? Like we run 100,000 of designs, we run the simulation, post-spec simulation, to verify which one is great and which one is not, and filter them. So your point is right, but you know, the goal here with open source is basically to explore this data-driven optimization for analog design. I don't think that has been tremendously, you know, explored, and I'll let you know when we get some results.
Okay, thanks. I just have one follow-up question though. I'm kind of curious. Do you ever check the parasitic extraction from Magic versus something like Calibre? I'm just curious how well they match.
I've done that work 2 years ago, but the issue is that you can decouple so you have to do like 16 or 4 combination of this. So basically, you have to extract the design using Calibre and then Magic, and then simulate them with a closed, like let's say HSpice, and then, or Spectre, and then go back and do the extraction with Calibre. I mean, you have the extraction with Calibre and Magic, and then run it with ngSpice. I've only done closed tools, completely closed tools, and completely open source, and the results are kind of different. For especially on corners, like an ambient temperature, you still get some good results. I have a table which is actually available publicly, but in -40 and 120 degrees, you'll get like wild results, like completely off results. So the reason behind that, I'm suspecting, is basically the models are not great at those corners. So we're trying to improve that with NIST. But there might be some extraction issues. Like for instance, at the time, the vSub was connected to everything, right? Like with Magic, you can extract the design. The substrate is all connected to all the transistors, so that's not good, right? So that's those are type of things we found out.
Okay, great. Thanks.
Yeah, no worries.
Anybody else?
Mehdi, this is Matthias speaking.
Hi, Matthias.
Okay. I wonder how you actually do top-level assembly of your tapeouts, because I mean, I imagine in open source world you have a lot of different methods and tools to produce single blocks.
Yeah.
Do you do this simply in GDS by putting together the GDS, or?
So the final assembly, you mean like this all blocks together, or at the top with Caravelle?
Yeah, at the top of Caravelle, or even this test chip thing you presented. So is that simple done manually?
So in this case, we have done all the tools we call it different tools, and I was mentioning in my presentation there's interoperability between these tools. Some of them use, you know, def-lef, some of them are using SPICE, some of them are, you know, just load the GDS in, like K-layout, or maybe I'm missing some part, you might tell me. So we had to create scripts, like Python script, to do parsing, which isn't great. It's not clean and it doesn't scale well. So I don't want to say it's all automated, but it's like a really painful step to do. So what I'm trying to do with my students right now is, instead of running everything separately, so basically if we get the, like let's say this is the control and this is the some logic you have here for the clock gen, then I'll just import them in GDS Factory or K-Layout and create some automated routing to it. And I think that would work best, you know, compared to just getting the pins here and try to connect them, generate a left of this guy. So there's different ways to do this. It's just that it's not great yet. One of the work I'm trying to do with the Google folks is basically to try and get K-Layout to call tools like Magic internally, or you know, ngSpice. So maybe you can tell me how that is possible, but those are ways we exploring right now.
I mean, the strengths of the commercial frameworks is that they provide us a single platform that you can do this on. And I think we only have, as of now, we only have, let's say, GDS, for example, to do that eventually. Yep. That's something I imagine is tricky to handle with a project with multiple contributions. Do you think GDS is actually a way of managing this, or would you prefer some other?
I think, you know, GDS is not great for doing this, right? You still need to have a connectivity. And so LevDef is kind of in the middle, but it doesn't have the front end of line layers. So something in between would be great. But I think if you combine the GDS and LevDef, that, you know, or some kind of Spice LevDef type of thing would be helpful. So, you know, like let's say we, with the arrays we are generating using GDS Factory. So I import them in Magic, extract the left. So I can integrate everything using OpenRoad at the top, right? But still, the limitation is power routing, because a lot of these things require, you know, wide connections and you know, very exotic routing. Let's call it that way. So that is not easy to handle right now. So.
Okay, I see.
Yep. Do you have a better way to do this?
Oh, no, I'm just mainly asking, but maybe it's something like annotated GDS or something like that.
Yeah, I mean, the Spice is a great, GDS Spice is a good way to do this, but OpenRoad doesn't understand the GDS. Like, there's no GDS to def parser.
Yeah.
I think there is one in Magic, but I've never tried it. But yeah, that's the current status.
But maybe that's something that calls for a joint activity, right? So defining something beyond GDS and beyond dev.
Yeah, I think that would be awesome. Like, coming up with a standard here to you know, to interface all these tools would be great.
Yeah, I'm open to discussion. So
sure, we should. Yeah. Yep.
I'm sorry, I have one question. It's Sergey. I would like to know about that's like a general question about the chip design. What is the possibility in your, how do you think about the AI in chip design? I mean, how much is possible to automate chip design process, and how much it can be automated? This is like what I would like to know more about, because of in last 2 years I see the tendency that lots of startups are going to be developed that using AI in chip design, but not the chip which has AI functionality in a chip design process. So the AI that can design a chip. So what is your consideration, or what is your perspective on this topic?
Yeah, so I mean, I've been following the literature, and I think Magical is using some kind of ML engine, but you know, it's a cool approach when you read the paper. I just believe it's not scalable. You know, the goal of my work is being scalable over different technologies and different test cases. So what I want to do is, I want to leverage tools like Align and maybe even Magical or other tools. If there's a framework that comes up of this bootcamp, then I would love to try it for my small auxiliary cells. The approach I'm taking is modular, right? Like divide and conquer, rather than take the whole design and route it all together. I think that's not feasible for everything. You can do it for a design or two. So what we're doing is generate, as I said, thousands of designs. I think that's the first step we want to be able to do. And when I say hundreds of thousands of designs, it's basically all DRC LVS clean. Then we can start developing some adversarial model or some genetic model to basically try to figure out based on the PEC simulation, what is the layout that makes sense. And then from that point, you can start going further. Like what is it in this design that makes it better, right? And then we can explore that route and see how we can make a design, how we can train a model that basically would generate, or those parameters that we give to this layout generation to give you the right model, taking into account the blocks that are inside of it. So it's I think it's a step-by-step thing. The open source community is great for that because you can leverage a lot of expertise and especially the software part or algorithm part. A lot of people are really good at software in our community, and I've been learning a lot working with them, and discovering new ways. Like for compilers, they're using a lot of interesting things to compile code or check which design is good, or like which RTL or which C code is good. So I would like to try and leverage those expertise in our world, and I'm pretty sure it's gonna get something good, or at least a step forward.
So it's possible to have an AI enhanced chip design tool. So generically, if we can say like that, so we will have in the future, we will have a tool for chip design which has AI enabled, and he is checking and verifying the design that you are doing and giving suggestions and fixing, like we can say, like during flow some errors, and giving more suggestions on optimizations. So I think in this way, this is like, for me, this is very good area to move on.
Yeah, I like your idea, actually, providing suggestions during the design steps,
yeah,
right?
Train with, the open source is like the basis for this, because you can train your AI using lots of open source lots of open source designs, and he can suggest you by them as an experience and say, okay, in the world, like suggestion that in this project they did such thing, you can optimize it this way and it can match these things. So AI can like be a supervisor when you are doing the design. So this is how I think.
Sure, I like the idea. I mean, it's just that it's hard to see to get which design is good. So I think post-spec simulation is the right way to go. But as this community is growing, I'm pretty sure we can get a good set of data, and AI is based on data, right? Like that's
Yes.
So yeah, I like your idea.
Okay, and another question is about in open source toolchain. I heard that we have some missing point which has only Siemens CDA. The open source alternative of that tool doesn't exist. But what is exactly, I mean, the name? Maybe you heard or know about that tool, because there is OpenLane, which is based on Yosys and uses also generates the GDS files, I mean the RTL synthesis and so on. But what we missing, what holes we have in open source toolchain flow? Do you know it? I heard that there is missing, and this tool is made by only Siemens CDA. So only Siemens CDA is have. Open source alternative doesn't exist. But I researched and didn't found it. So there is Calibre, there is other like Multisim and so on. but I doesn't know in Armenia. I'm from Armenia generally. Here we have we had Mentor Graphics, which now is Siemens EDA, and they are working on Calibre. And I have contacts with them, sure, in people inside and top and in the group managers. So, but I would like to know what is that tool? What the name of that tool?
What the name of the tool you
We
mean?
are in open source. We are
Oh, okay. So we have NetGen for LVS, Magic for PEX extraction and DRC, and now we have K-Layout doing DRC, and I think maybe we can have LVS in the future. I don't know. You know, I compared at some point.
We do have LVS.
Yes, we do have LVS. Sorry, Matthias, I'm not up to speed on everything, but
it's lacking parasitics. That's definitely not there.
Yes, correct. Got it. So basically, in Skywater, we have mostly everything. You know, some of the things I want is V2 LVS. We can do that using some tricks in Yosys versus some other tool. I forgot which name it is. But if you want to move to another node, then you know it gets a little more complicated. And I feel like K-Layout is the solution for that. Maybe Matthias doesn't disagree, but maybe you can come up with a new this tool. But I don't feel like it's you know, it's a roadblock. Like let's say if I want to tape out in GF12 right now with the open source tools, I can just do it using the rule deck from the Foundry or like the DRC LVS rule deck. So we need to find a way where we can import those rule decks in K-Layout and Magic, and it should be doable.
I mean, to comment here, the problem is IP protection because the SVF language by Calibre is owned by Mentor, and they are very picky about implementing it elsewhere.
So what is the solution for that, right? Is there other ways to do?
Yeah, I mean, the solution is basically that you do not write LVS or DRC decks in a specific dialect, but you generate it from tables or something like that. So some generic way, and then you can generate it for different target.
Yeah.
I mean, unfortunately, I think that Mentor pays a lot to the foundries to only supply SVF rule decks.
I heard that tool is regarded to physical level design or something like physical design. So it's not just a Verilog synthesis. No, not that part. It comes close to the fabbing, I mean manufacturing process.
Right.
But I don't know the correct name of which is the Siemens EDA tool, which doesn't have alternative in open source and which is very important for us to have it, and we don't have that.
I think
maybe
Calibre. I mean, Calibre is everywhere, so it's a de facto standard for verification and parasitic.
Physical verification, right?
Yeah. Physical.
Yeah.
I know the guys from the Siemens EDA in Armenia, which they are working in Calibre, and they are very strong people, physicists, and they are Armenians. I have direct contacts with them. Maybe I can somehow contact and some bridges to start some overviewing of generally how we can develop the open source version of Calibre, because they know good Calibre. I mean, they know I think they should know all inside, and they can like overview the specification if they will not start helping a coding level, but overviewing the like task level. Maybe they can help me or help our community, and we can have some alternative to Calibre. Maybe they can, I don't know, I don't promise it, but this is, I think, possible, because in Armenia it's like very small community here of the EDA, so everyone knows each other, and maybe I think they can help us, help me generally, and then I can share with you, and we can have some project that doing that the physical level. It is like physical level verification or physical layer verification, such so that it doing like thermal analysis, power analysis, and giving all in one, like, how can I say it, like a log file that is your design correct or not? Is it meets to the rules or doesn't meet? So it analyzes all overall projects, entire, like it can analyze entire SoC, and it's like very huge. If it's Caliber, it's a huge tool, and I can find some insiders who can help us. This is like a general info. I am not like going to have a bad to say bad for their business, but I have some connections, and maybe they can be helpful because they are computer scientists, physicists in semiconductor, and they are really good guys. They are old. I mean, they're more than 40 years old people, and they work in that field like 20, 30 years. So they have huge experience in this aspect. So I think I can find some help from their side, and we can overview. The most the difficult thing is to overview project until the task level. If we have that, like the management part, like PM part, then the tasks and to find coders and do the coding actual, it will be more easy actually, because we can share it to universities over the world in a GitHub, and this can be like achievable. But the problem is to divide the whole project into the milestones and tasks and so on and so on. I think this is the problem, because of they know the inside of Caliber and bare bones of Caliber.
Very careful here, because the problem is not coding. The problem is the ownership of this
the algorithm and so on.
And you cannot create open source that reads the rule text from Caliber. That's, I mean, that's eventually that they are so protected.
You have to develop first an open verification language or something like this.
That's the point.
So if you define this, then you can start working on tools using this verification format.
And these tools are available. I mean, also Magic has LVS and DRC integrated, but it's not the tool which is not available. I mean, Caliber is a very good tool in terms of performance and functionality, but it's not unique in terms of being the only tool that supports it. But what is unique is the verification language that Caliber comes along with, and that is protected. All foundries, they only use Caliber, or they mainly provide Caliber decks and not third-party decks. That is the problem.
Okay, I must be very careful, because I should sure I will be very careful, and I will start to understand, as they are scientist people, they will share some understanding of what's going inside. So the problem, as you mentioned, is the language. So we need to develop a language first, which then doing that all like JavaScript for web development in a browser. So it should be specific language for only that such tasks.
That is a project worth pursuing. But then you also have to convince the foundries to use that format.
Okay, so they have agreement with foundries. They are giving the assurance that this is 100% working tool, and you can do 100% technology that can meet up your needs. And so there is also the political part, that you should talk with foundries and make them legalizing your language or your tool to work with their production. So okay, this is two parts. So one is a technological part, another is the it has such a political part, to have agreement with them, to come to agreement that okay, they are agreed to use this, and they are recognizing it. Recognition process problem.
No, it's a question of what is the reference flow of a foundry. So a foundry has to define the primary tools for each step, and then this is the reference flow they also use for the development of a new technology. So, and then this is normally what they call, so TSMC calls this the golden standard, what they have. So, and for example, first is they release all the caliber run sets, so DRC, LVS, and so on. And later on, they provide then also for other tools, so like PVS from Cadence, for example. So, but this is only, or they make then the release process and the qualifications then always against their golden reference standards. So this means if the PVS run set is, or the results are close enough to the caliber results, then it's fine. So it's not then separate, it's only, it needs to be comparable to the reference results. And I think this is the same in each other foundry.
Okay.
And yeah, to reduce the
So
effort.
as I understand, it depends foundry or not?
Yeah, yeah. Each
depends.
foundry defines more or less their own reference flow. So,
okay.
and
So
normally the best for a foundry is to look what are the most tools used in the industry. So, and then yeah, most of the customer are very close to their own reference flow, and this means at the end with the first run sets they release, most of the customers can work.
Okay. So in our case, we are focusing, as SkyWater provides open source PDK, so it should meet to SkyWater's references and as a starting point. So then comes IHP and in Germany, and they are also open it. I think it was also 130 nanometer, and then GF, which is open like 180. As I heard, they open, as I remember, 180 nanometer. But yeah, okay, it's big for nowadays technological. It's a little big, but whatever, we have what we have. So we need like to give our thanks to them to give us such opportunity. So okay, with SkyWater, I mean, how it is possible to have such a, I mean, is it defined by SkyWater already defined, or it should be starting a negotiation process and understand the process of the references? I mean, is it available now, that reference, or it should be developed? This is my question.
I think that question should go to SkyWater. I can put you in contact with the right people.
Okay.
Shoot me an email. So I'll just put it on a chat here. But I can try to do the connection there. I'm pretty sure SkyWater would be open to things like that. But I can talk in their behalf.
I mean, to my knowledge, SkyWater basically provided a caliber deck for reference, but it's not public.
Yes.
Okay.
But I think that when Google open sourced it, they have re-implemented the rules. We are in Magic mainly, but only a small subset, to be honest. But Global Foundry, when they open sourced the 180 nanometer PDK, they provided K-layout rule decks for LVS and DRC, and no K. So they are, that's their reference flow, if you like.
Yep.
Okay. Okay.
All right.
So this is like our last thing. So I mean, do we have any other technological, I mean, in the tools aspects, any missing piece except the caliber like?
I mean, they're pretty sure there's other things that I'm not using, like let's say TCAD, for instance. But you know, the good thing about open source is that we're not set by these rules, right? We can create our own tools depending on the needs. So I don't want to restrict the horizon by defining a closed approach, right? Like the SVF format or whatever other format we have. So the goal here is to try things in a different manner, and maybe we'll get to use the same approach then as closed tools, but let's try other things first and see.
Okay, so from your side, the next thing will be design chips using open source tools, or making open source tools even better, like improving them. So what will be like the most most needed in the community or in the market? How you want you can say it, but I mean, what will be the major trend? Will be designing open source chips with open source PDKs and manufacture them with using existing tools, or improving the existing tools to make more more powerful or
yeah, I understood the question. So what happened for us is we are at the boundary, right? We are at the forefront, and we get stuck with the tools. Some of the time we are able to do it, some of the other times we are not doing it. So for instance, the ECO flow was a good example. A lot of the designs that you may have heard on a PW2 had hold violations. So we kind of expected that, since MPW1, and we created the ECO flow for that. So, and when I say created the ECO flow, that means we went to the code and sent a pull request to these tools. Regarding OpenRoad, for instance, like we needed voltage domains or visioning in physical design. So these things were important for us to keep moving forward. And we'll keep doing that. So we have a team that is basically a mix of EDA people and circuit people. And hopefully we're going to keep pushing this forward. And hopefully you guys can help us do that as well.
Thank you.
Sure. All right. Well, thanks everyone for having me. Thanks, Mirjana, if you're still there. And good luck with your bootcamp, and great. I think it's a great work you guys are doing. So keep up the great work. Bye-bye.